Hi everyone. Today we need to write the example session of the week 8, or in a manner the discrete Fourier transform examples. Okay? So in the first place, we need to write a code the n times DFT for Dirac and unit step signal. Okay, this is the first example, week 8 code. So first of all, to define the n in here, or setting to any points or positive integers in here. Okay, and so I should drive this value with in terms of the sampling rate of the R frequency, because it is our limit to catch the R points coming from the embedded system or computer or the some measurement device. Okay, and so we need to create the t or time values in here with the step of the 1 divided by fs and 1. Okay, and so we need to take the transpose of these terms, and so we need to fill the row values, not the column one. Okay, first of all, we need to define a Dirac delta function, or in other terms a impulse for n. Okay, so the x can be settled with the zeros and 1. This the n times 1 matrices. Okay, and x1 can be assigned with the 1. Okay, and so the first element must be 1, because this is the discrete form, and so we need to create the impulse response with the with the 1 value, except to 0. Okay, and so we can assign at the index of the 0 as 1, and then the rest of them should be 0. Okay, and so we can create the W matrix in here to create DFT matrix in terms of the n and x and t. Okay, this is not the standard matrix, predefined matrix, but we need to we need to apply it. Okay, or we need to write it in here. So the function w should be returned to to create DFT matrix in here, just like this one, and so n, x and fs. Okay, these are definition for the matrix representations. Okay, and so we need to give the n, x, which is given in here like this one. Okay, and so this n must be equals to the length t. Okay, this is the x, and also we need to give the fs in here. These are the definition. This is the number of points taking from the measurements, and so this are the input vector in here like this one, and so the fs is the frequency rate of the sampling. Okay, and so this function can be defined with these terms, and also we need to define the n other terms in here, just like this one. For example, in the first place, we need to create the matrix of this one. W is to n times n, right? Because the discrete Fourier transform should contains n times n matrices. Okay, for creating the periodicity on the Euler identity form. Okay, and so we need to populate the DFT matrices, and so for k beginning with the 0 to n minus 1, and for n is equals to 0 to n minus 1. Okay, and so the end should be given in here. These are the creation of the matrices in here. We are filling the values of this term. W, k plus 1, n plus 1 can be assigned with with the standard definition of the R function. Exponential terms minus 1i times 2 times pi times k times n divided by normalization value n. This is the point of the what? Total points. And so after that, we need to take the what? The v times x divided by n. Okay? So these are the matrices, and w x can be created to what? To discrete Fourier transform in here. The x is the what? The DFT matrix. Okay? No, DFT results output. Okay? And we need to divide the what? The divide by n, which means that we normalize the whole the results in here. Okay? And after that, we need to give the what? The frequencies of these terms. And so how can we do that? We need to create the what? The 0 to n minus 1 times fs divided by n. We should take these values based on these informations. Okay? So these are the complete frequency ranges in here. For example, if we have the 100 points in here for the what? For the 1 second, and so we can take to what? The 100 points, which means that we can reach to what? 100 hertz. Okay? But Nyquist criteria limit us or bound us to what? To divide by 2 of these frequency values. Okay? And so we need to give the what? The idx in here, which is equals to the what? The frequency value smaller than equal to fs2. Okay? And so after that, we need to create the figures in here, just like this one. And so the stem, the frequency, and so idx, this is the index of the what? The 0 to 50. And so the absolute value should be taken in here, just like this one, x, and also idx. Okay? Because the Nyquist criteria tell us the, if we set the 100 in here, and so we can search to what? The 0 to 50 frequency ranges in here, just like this one. Okay? And so this stems is given by in the what? In terms of the such a line with the points. Okay? This is a special figure. And so the title of the magnitude of DFT up to fs divided by 2. Okay? And so x label can be assigned with the what? The frequency values of the what? The hertz, and y label should be assigned with the what? The absolute value of these terms, x f, but in the absolute form. Okay? These are code for these things, and so the grid-on should also be calculated in here, just like this one. And so if I run this code, and then we will have I'm sorry, xnn, I'm sorry guys, this should be changed with the what? With this one. Okay? And so we have the what? This line in here. The frequency range is to what? Is always the same with the values of the what? The 0.01, which means that we have the 100 points in here, just like this one. And so if we don't normalize this signal in here, and so if we rerun this code, and so we have the 1 values in here. This is a direct impulse response, which means that this returns to the what? To the Euler identity formulation, just like in the previous examples, which is written on the what? On the notes. Okay? This is the Dirac delta impulse function results for the what? For our algorithms. Okay? But we need to normalize the hard case, because we need to do that. And so this is the first case for the what? For these things. But if we create the what? The another terms in here, for example, the define unit step signals in here. And so the x must be once length t1. This is the unit step signal representations. Okay? And so we can call the what? This function in here. Okay? And so if I run this code again, and then we have the whole values in here is 0. See? 5 Hertz, 10 Hertz, 15 Hertz, 20 Hertz, 25 Hertz, 30, 35, 40, 45. But we have the 1 value at the 0 frequency, which means that the unit step signal possesses the 0 frequency components in here. Okay? This is the basic implementation of the n times n creating DFT matrices. And so you can easily apply this code up to now to create your embedded code, C or C++ code. But in the Matlab, we can use some predefined function. But if you want to create your DFT application in here, and then you can use this syntax in here. For example, this is the this is the unit step. For example, we can define the frequency signals, define a sinus for the the f can be equals to the 1 and x sin 2.pi.f.t plus, for example, sinus 2 pi 4 f t. Okay, and so which means that this is the f1, this is the f2 for simple manner f2. Okay, and so if we apply these inputs in here just like this one, we need to see that we have a peak values at the at the 1 and 4. Okay, and so if I run again this code, and then we will see that we have the 1 values in here just like this one, and also have the 4 values in here just like this one. Okay, and so what about if I choose the 20 values in here? And so if I rerun this code, and then we can see that we have the magnitude at the highest values at x19.802. Okay, and so we have also the 1 Hertz value at the at 1 Hertz. Okay, this is how we can build our own DFT matrices based on based on this information. But what about the 100s can be taken in here just like this one? And so if I rerun this code, and then we will see that we have only the 20 Hertz signal, which is higher in here, but not the 100 one. But why? The reason is simple. The reason is that we cannot take only the values of the up to Nyquist criteria, or the fs divided by 2, which means that we can take the only 50 Hertz frequency values in here, not the 100 one. We cannot observe that this signal in here. Okay, this is the first example of the the R signals in here. Okay, and so how about how can we create our own symbolic toolbox matrices in here? This is another important parameters, m times DFT matrices in symbolic toolbox. Okay, so and maybe 8, and so we can define the sims x1, x2, x3, x4, x5, x6, f7, x7, and x8. Okay, and also we need to give the real values in here, because this must be in terms of the real. Okay, and so x can be defined with the the x1, x2, x3, x4, x5, x6, x7, x8. Okay, these are raw values. 8 times 1 rows can be created in here just like this one. Okay, and so we should to give or create the w and x values in here. Create DFT matrix n and x. We need to implement discrete DFT matrix to to display the values of the symbolic DFT matrix W. Okay, and so we need to give the pretty simplify W terms in here, just like this one. Okay. And also we can observe the results of conjugate results. And so in order to get the conjugate values of this matrix, W transpose times W divided by N should be given in here, and pretty simplify the result conjugate. Okay, and so the function should be created in here. W and X can be written as the create DFT matrix in terms of the N and X. Okay. These are the function. So firstly we need to create the sims N and K in here, and W LM should be created with the exponential terms of the minus I times 2 times pi times K times N divided by N. Okay, and so W can be created with the symbolic matrix with the zeros N times N. Okay, this is the initial condition of this W matrices. And so the for K is equal to 0 up to N minus 1, and for N which equals to 0 to N minus 1. Okay, and then and should be given in here. W K plus 1 N plus 1 should be assigned with the substitution of the L. Okay. This function should be given in here. Okay, we can populate whole of the matrices based on these informations in here, just like this one, because we define the N and K in here, and so this K and N updated at each element of these terms. Okay, and so X, or the output of the DFT matrices, W times X divided by N should be given in here. Okay, and so firstly I think we need to begin with the simple examples. 4 can be given in here, and so the 4 can be given in here. Okay, and so if I run this code, and then the symbolic DFT matrix W is equals to 1 1 1 1 1 minus I minus 1 and I, and 1 minus 1 I be 1 minus 1. Okay, 1 I minus 1 minus I, and so the resultant conjugate matrix is equals to the transpose time W, which means that this transport is equals to the inverse values of these terms, and which means that we have to the unity or the identity matrix in here for the for the 4. But for example, if you want to implement this algorithm in the higher order values, for example 8, and so if I rerun this code, and then we can see that our matrix can be built with with in terms of this one. And so just remember that in the lesson we will talk about the 360 value divided by 8 gives us the 45. Okay, and so these values are the remainder of are DFT matrices, and so we can split the Euler identity formulation or the graphical representation up to up to 8 parts, and so we will deal with or combine these algorithms or the values with with this part of study. Okay, or this part of the line in here. For example, if I choose the 6, which means that we have the 90 degree 60 degree in here, because 360 divided by 6 gives us the 6 region. Okay, and so if I rerun this code, and then we will have these formulations in here. Okay, and so always we will get to identity matrix in this form. And so we can create our own DFT matrices in the symbolic toolbox. It's useful to what? To build your algorithms in the what in terms of these populations. Okay, and so if we have this information, and then we can build our own algorithm for the discrete Fourier transform, and then we will use it in the mathematical formations. Okay, this is the easiest way to create your DFT matrices. So what about to another algorithms in here? Maybe we may utilize the short time Fourier transform. This is Windows based transform, and it's different from the discrete Fourier transform, but with what? In the short time Fourier transform, at each step we search some pattern, some window in here. For example, if you take the 1 to 1000 data, and so at the short Fourier transform, for example, 1 to 50 is search for the frequency. In the second place, 251. In the third place, 352. In the fourth place, 453, and goes on up to what? Up to this number, 945, 1000. Okay, these are basic algorithm for for utilization of our discrete Fourier transformation. But how can we do that? We need to give some basic pattern for this algorithm in here. Okay, and so this window must also be created in here, just like this one. Okay, so as always we do fs 100 and t, for example 0, 1 divided by fs and 10. Okay, and f is equals to 1 and x sinus 2 pi ft plus sinus 2 pi 5 ft. Okay, and so we can use the window type, but we don't need to use that because we create our own short time Fourier transform. And so in order to create the short time Fourier transform, we need to at least create the double times fs in here, because we search to hold the parameters for a Windows based method. For example, if you have the 100 values, and so we need to create the 200 values for this periodicity, because each segment created up to 1 to 50, but in the first place we need to take the minus 49 to 1. Okay, and so we need to create or build up to 2 times creation in here. Okay, 2 period of signal must be written in here. And so if we take these values, and we can build the create DFT matrix for SDFT with the n values. Okay, and so we can create the segment value in here, for example x1 to n, for example in here, just like this one. And so if we have this value, and so 1 to 200 values is evaluated for this segment, and then this segment must be multiplied with the w times segment, and so we can create the x values in here, just like this one. In order to get the frequency values in here, we need to create the frequencies up to 0 to n minus 1 times fs divided by n. Okay, these are the basic creation of the frequency periods. Okay, and so idx must be assigned with the frequency is smaller than 2 fs divided by 2. Okay, and so the figure must be built with the stem figure. The frequency is idx and absolute values of the x and idx, because we have the real and the imaginary parts of the x in here. And also we need to create the what? The hypotenuse coming from this one. And so if we take the absolute values of this term, we can observe what the magnitude of this signal, even if it is written in the what? In the imaginary part of the signals. Okay, otherwise we cannot observe that. So after that we can take a copy of these terms in here, just like this one. Okay, and so the uncomment x label, y label, and read on. Okay, so how can we build the function create DFT matrix for STFT with the values of the n? Okay, and so the n should be given in here, just like this one. And so creating the DFT matrix for STFT analysis, we need to determine we need to use the n values in here. And so we need to create a window based method in here, just like this one. In a standard nomination, we can use the window type in here. For example, the Hamming, Han, and some other methods for especially the filtering operation, especially for the IR or FIR, finite or the impulse response filter design. Okay, but in this case we can build our own window, the ones and one. This is created for the what? For the n times 1 value, which means that this is a rectangular window in here. And also we need to create the w zeros n times n. Okay, because if we take the application of this signal fs up to the 1 to 100 or the 200s, and so it's our segments in here, just like this one. And so we need to create the 200 times 200 w matrices in here. Okay, and so how can we implement these algorithms? For k is equals to 0 up to n minus 1, for n is equals to 0 up to n minus 1, and and so the w k plus 1 n plus 1, the window of n plus 1 times exponential terms of the minus I times 2 times pi times k times n divided by n. Okay, this is the R creation of the DFT matrices. Okay, this is simple, just like that. And after that, if I choose to implement these segments, and so we will see that we have the x is the 1 values in here, and also we have the x at 5, 1 frequency, 5 frequency, f1, and f2 can be given here. F2 is the, for example, 25, and so is the 5, for example. In this case, we can create these matrices in here, just like this one in the first segments. Okay, also we can search another segments in here, for example, n 2 times n plus 1. Okay, so if I rerun this code, n I'm sorry, I think it's a problem. Hmm. 201. Okay, so minus 1. This is the dimensionality problem in here, guys, don't worry. And so 5 and 25 is given in here, but at the at this period. Okay, and so we can use this technique to analyze each splition of the are signals. Okay, and so we can apply the different matrices in here, just like this one. For example, if we use for example, x up to 1, 2, 2 or 500 can be assigned with the zeros. Okay, maybe. And so if I rerun this code and then we have the zero values in here. But why? Because the n is coming from the what? The 100, no, 200, and so 400. And so we cannot contain any signal in here, just like this one, because the figure plot x and t can be given in here, just like this one. And so see that we have this signal in here. I'm sorry. And so we have the 5 seconds values is what is equals to what is equals to the 0. Okay, so we can update to 100 0, and so for example 200 to 40 values can be assigned in here, and also for example 600 to 500 must be with what? With the 1. Okay, and so if I rerun this code, and then we can see that we have this period in here, just like this one. Okay, and so we have the 0 0 and up to what? Up to 100, which means that the first 100 values is assigned with what? With the 0 values. Okay, and so what does it tell us? Our algorithms, and then we can start with the some points in here, just like this one. Okay, and so we can create what? The n matrix n in here, n minus 1 or the n up to this one. And so if I rerun this code, and then we will have these magnitude values in here for the what? For the zeros values in here. Okay, because we have the what? The 1 to 200 values in here. Okay, and so see that 1 to 2 contains the what? The frequency components of this signal. But what about the 200 must assign to the 0 in here. And so if I rerun this code, and then we will have the what? The 0 values to what? To this period. Okay, or 500 to 70. I'm sorry. It's the dimensional problem. And so see that the 5 to 70. And so this 5 to 70. We have some impulses in here, but we don't have the total number of the what? The R frequency components, right? Because we don't have any signal in here. But after the what? After the 7 to 8 in here, 7 to 800, and so we can reach the what? The total number in here. I'm sorry, we have problem in here. The x segments is to what? 900. Okay. I'm sorry guys for this case. And so we can create what? The 100 values of the what? Of these nominations in here in the stem graph. Okay, and so in order to normalize the higher values in here, and so we need to add also the n values in here. Okay, just see 0.5 0.5, which means that we have two components in here with the absolute values, or the Pythagorean values of the what? The 0.5 0.5, but at each specific region we don't have the what? The frequency characteristics. Okay, this is the short Fourier transform, and this is the simple example, but you can easily apply this function on the what? On embedding code. Okay, so these are the code implementation from the scratch, but the Matlab also possesses the what? The sum function definition for creating the what? Creating the discrete Fourier transform. Okay, especially for the fast Fourier transform in Matlab. For example, the fs 1000 and t sampling period can be created with the fs, and L can be defined with the 1500 in here. This is the length of the signal, okay? Length of the measurement. And so the t, the time vector, can be built with what? The 0 to L minus 1 times t, okay? And so, for example, the x can be built with what? The 0.8 plus 0.7 times sinus in here 2.pi.50 times t plus sinus 2.pi.102t, okay? And so the plot is in here 1000 t, x can be given in here, okay? And so the x label can be built with the what? The t milliseconds, and y label is assigned with the what? The r x signal, for example. So if I rerun this code, and then we will have the r basic utilization in the what? In the millisecond period in here, okay? We have the complex signal in here, sinus and cosinus can be built with this one, okay? And after that, the Matlab gives us the FFT function, y FFT x in here, just like this one, okay? And so if we rerun this code, and then the y complex double values is built with these nominations in here, okay? And so this is the absolute form of, or this is the magnitude form of the what? Our Euler identity formula. This is spherical or the circular coordinates of the R signals. And after that, just remember that we need to create the PQ. The normalization and removing the negative frequency must be yielded with in here. Y divided by L should be applied because we have the 1050 points in here, and so Y is the R ratios of the what? The R FFT transformation. And so we can take the what? The absolute values of this term, and we can reach the what? The magnitude, okay? And so P1 can be assigned with the P2, and so 1 to L divided by 2 plus 1, right? And so the negative frequency is expressed from here, okay? And after that, P1 2 to end minus 1 should be replaced to P1 2 and minus 1, because we have the negative frequency in the Euler plane. For example, 1j and minus 1j is the same frequency period, and so we need to take the double times of these terms, because this is the fast Fourier transform, not the discrete Fourier transform. This is also discrete Fourier transform, but we have the some different processing here, okay? And so the f should also be contained with the what? The fs divided by L times 0 to up to what? L divided by 2, okay? And so the plot should be taken as in here, just like this one. The line white should be assigned with a 3, and so the title, this is the single-sided amplitude spectrum, okay? The x label is in terms of the what? F hertz, and y label is the magnitude values, okay? And so if I rerun this code, and then we will have the 0.8, 0.7, and so the 1 values in here, but at specific frequency values of this term. Just remember that we have the limits of the 500, because we have the sampling rate at what? 1000 hertz, okay? But see that the amplitude of this signal is 0.8, because we have the unit step signal in here, and 0.7 we have the what? The 50 hertz values at what is 0.8. And so this is a sinus signal with the amplitude of the 1, which is given in the what? In the 120 values. But what about 0.2? Times values should be given in here, okay? And so we can reach what? The 0.2 values in here. Okay. And so what about the 2 in here? And so if I choose this section, and so the single-sided amplitude spectrum can be given at what? At the magnitude of the 2 value for the sinus signal. Okay, and so if I choose the cosinus values in here, just like this one, and so we have also this signal in here, but the other terms is, for example, this is the 1, this is the 2, and this is the 3. Okay, so if I choose this implementation 1, 2, 3 is given in here. Whatever this signal is sinus and cosinus. Okay, and so if I rerun this code, and then we have the magnitude of these terms. Okay, because the cosinus and the sinus is the perfect representation of what Euler identity formulation. Okay, just see that. And so this is how we can build what FFT algorithm in the Matlab. Okay, and also we can build another algorithms for the multiple signal representations. Okay, so it's the X5 FFT for multiple signals. Okay, and so this is the same with the previous one. Okay, I can take it and comment. Okay, and so the x1 is the cosinus of the 2 times pi dot 20 hertz times t. Okay, these are the basic algorithm. And so the x2 and x3, and this is the 40 values, and this is the 50 values. Okay, and x can be created with what the x1, x2, and x3. This is the raw representation of the column values of this signal. And so the figure can be built with what the plot I 1 to 3. Okay, I is equal to the 1 to 3, and subplot can be given in here 3 1 I, and plot t 1 to 100 x I to 100. Okay, so are the basic representation of what are signal. And so the row plus num2 stri plus in the time domain. Okay, so the end can be given in here. Okay, and so if I rerun this code, and then we will have these nominations in here, just like this one. The title is given in here, the subplot I is assigned with these values. Okay, and so this case can be assigned with what? With this nomination. Okay, so I'm sorry, this L is 1000 in here for these times, x1, x2, and x3, and c. And so if I rerun this code, and then we will have these nominations. Okay, so after that we need to apply the dim2 in here, and y can be applied with what FFT x, L, and dim. Okay, it's the dimension of this signal, the FFT, the second order, or not second order. We have the 3 different signals, and so we can use the 2D FFT transformation in here, just like this one. And so the P2 can be utilized with what the absolute values of the y divided by L, and P1 can be assigned with what the P2 whole values 1 to L divided by 2 plus 1. Okay, and so the P1 whole values 2 and minus 1, and 2 by 1, and 2 and minus 1. Okay, so the figure can be given in here just like this one, and so this plot must be changed with the what, the 0 to fs divided by L is the step rate, and after that fs divided by 2 minus fs divided by L. Okay, and so P1 I value 1 L divided by 2. Okay, this is the frequency representation of this domain in the 2D formats. Okay, and so what about this case? It's the problem of the R codes. Okay, and so if I rerun this code, and then we have the 3 signal in row 1, row 2, and row 3, and so we have the 500, and so we can search the 100, 200, and 300. It's more observable for our case. And so we have this signal in here, this signal, and this signal, and so 100, 200, and 300. Okay, and also we can multiply with the 5 and 4 and 2 in here. And so if I rerun this code, just see that the magnitude of the signal 2, magnitude of the signal 4, and magnitude of this signal is the 5. Okay, this is the basic implementation of the fast Fourier transform in the Matlab programming language. Okay, that's all. These are the whole case related to what the discrete Fourier transform in the Matlab implementation of this code. And so x4, x3, x2, and x1, especially for the 1, 2, 3 examples, can be implemented in the in the embedded system, on the embedded system. Okay, just remember that this is so simple. Just see that we can use anything in here for the short time Fourier transform, for the time varying signal, or we can analyze the total signal using the DFT matrices in here, just like this one, guys.